Hello class. In this video we're going to extend what we know about inverse variations and reciprocal functions, and we're going to extend it to the world of rational functions. But first let's talk about a little bit of review. Determine the four properties of reciprocal functions. This of course being domain, range, vertical asymptotes, and horizontal asymptotes. Now of course when we do this with reciprocal functions we always start with our transformation. So we have x minus 3 in the denominator. That means we are moving right 3. Oh boy, that's ugly. And then we're moving up 4. Now, there's a 12 in the numerator now. That means we have a vertical stretch by 12. But that doesn't actually affect our domain, range, vertical asymptotes, or horizontal asymptotes. So right 3 means our vertical asymptote is at x equals 3. Sorry, I guess I'm having a bad handwriting day. And then horizontal asymptote would be y equals 4. So of course we use the vertical asymptote to form our domain from negative infinity to 3. And then 3 to infinity. And then we use the horizontal asymptote to form our range. Yeah, I'm not having a very good handwriting day. I apologize. I'll try and get better. So let's use polynomial division to compare the given rational expression to a reciprocal function. Because right now we don't have a reciprocal function. We have an x in the numerator, and that's different. That's something that we haven't really seen yet. So let's use polynomial division. I know you guys are all in favor of synthetic division, so we'll start with synthetic. So I'm dividing by negative 1/2. And I've got 6x. So I'm going to put a 6 here, and I'm going to put a 0 here. Okay. Drop the 6. And this is pretty short. Negative 1/2 times 6 is negative 3. And then we add, and we get just negative 3, and that's our remainder. Okay. So this is just a constant. This 6 is just a constant. And so this function can convert to a reciprocal function, which would be 6 plus negative 3 over 2x plus 1. Okay? And you can say 6 minus as well. All right. But if we look at it, this seems now like something we're used to seeing. The only major difference here is this 2 next to the x. But this looks like the rational functions we've been dealing with. So what we started with was called a rational function. If we think back to polynomials, a rational function is a function with two polynomials, one in the numerator and one in the denominator. So we're talking about whole number exponents. We're not talking about negative exponents. We're not talking about square roots or anything like that. We're just talking about two expressions. These are two linear expressions, but linear are still polynomial. So that's the new term of the day, is rational function. A reciprocal function is a type of rational function, but not all rational functions are reciprocal functions. So let's talk about how to determine vertical asymptotes. Now we're used to using our transformations. This one was from the closer the other day. This was right 3 and up, or sorry, down 1. Yikes. Down 1. And so our vertical asymptote specifically was at x equals 3. Okay? But if we look back at our previous example, we've got a left 1, and we've also got a horizontal stretch or compression. So we got something else going on. So what's a universal way we can look at finding vertical asymptotes? Well, vertical asymptotes occur whenever the denominator is equal to 0. And so there's an algebraic expression that we can, or an algebraic method we can use right away. We're going to take our denominator and set it equal to 0. And this is very trivial in this case to solve for 0. So we take x and we add 3 and we get x equals 3. And lo and behold, we got the same thing. This is the method we're going to be using in class moving forward because we won't always get nice expressions like x minus 3. We could go back and do it with this expression where we take 2x plus 1 and set it equal to 0. And we would subtract 1. We got 2x equals negative 1, and then we'd have to divide by 2. And we get x equals negative 1/2. Lo and behold, same number we divided by when we did synthetic division. All right, so let's talk about vertical asymptotes. Now we have a quadratic in the denominator. Well, quadratic in the denominator doesn't affect us. Remember that when we take quadratics and set them equal to 0, we can use diamond math. You can also use quadratic formula if you so choose. I'm going to use diamond math in this instance because I think it's easier. So 12 and 7. And so our two numbers would be 4 and 3. So factoring the quadratic, we get x plus 4, x plus 3 equals 0. And then in the solving process, this is where we would set x plus 4 equal to 0 and x plus 3 equal to 0 using the zero product property. So I'm going to save myself a little bit of time. We get x equals negative 4 and x equals negative 3. So for a quadratic in the denominator, there we go, we actually have two vertical asymptotes. So let's go ahead and go over this one together. We have x squared minus x minus 6. So let's again, set the denominator equal to 0. And notice I didn't do anything with the numerator, okay? The numerator will come into play one day, but it's not going to come into play today. So for now, we're just going to ignore 5x. We're just going to set x squared minus x minus 6 equal to 0. Again, use quadratic formula if it's more comfortable for you. But I'm going to use diamond math and factor because I know these are factorable. Negative 1 in the denominator, and so we get negative 3 and positive 2. So x minus 3, let me make that a little bit neater, minus 3, and x plus 2 is 0. And so x minus 3 equals 0. That would give me a vertical asymptote at x equals 3. And x plus 2 equals 0. That would give me a vertical asymptote at x equals negative 2. So go ahead and pause the video really quickly and give this one a shot, and then we'll go over it together. Okay, so 2x squared plus 11x minus 6. Now, remember, when we're factoring this, we're taking the lead coefficient and we're multiplying by negative 6. So negative 12 and 11. And then our two answers would be, let's see here, negative 12 and 1. Nope, negative 1 and positive 12, pardon me. So we got x plus 12, x minus 1. And we're going to do our division at the end. So we get x equals negative 12 from this one, and we get x equals 1. But we started by multiplying by that 2. So don't forget that last step. X equals negative 6, and x equals 1/2 would be my two vertical asymptotes. Okay, so now let's talk about horizontal asymptotes. I put or other asymptotes, but at the end of the day, we've only been talking about horizontal asymptotes. We can leave the others. I just want to give you the criteria. And there's a lot of words on this page, so let's just try to take in the words for what they mean, and then we're going to go over some examples together. Determine the degree of the numerator, we'll call that A, and determine the degree of the numerator, we'll call that B. If the degree of the numerator is greater than the degree of the, if the degree of the denominator is greater than the degree of the numerator, then y equals 0 is your horizontal asymptote, okay? So this is saying the degree of the numerator or denominator, that's b, is greater than a. If b is greater than a, then y equals 0 is my answer. Okay, we're always expressing horizontal asymptotes as y equals. We're going to continue that. Now, here's the one that we won't need to know so much today, but it's worth putting in for completeness sake. If the degree of the denominator is less than the degree of the numerator, so that would be b is less than a, then there exists an alternate asymptote that can be determined by using polynomial division. That would be your choice, whether it be synthetic or long. I've often found that in these cases, long division is probably best. So b, kind of just keep that in the back of your mind for now. We may go over it in the future, we may not. But A and C. So if the degree of the degree of the denominator, I can't speak either. Can't speak and can't write. If the degree of the denominator is equal to the degree of the numerator, the lead coefficients of the numerator and the denominator will be the horizontal asymptote. So there's a lot of words there. It doesn't really tell us what our answer is, but let's go over some examples. Okay, so the horizontal asymptotes. We're going to look at the degree of the numerator. Well, the degree is the highest exponent, and that's an exponent of 1 right there. So the degree is 1. The degree of the denominator is 2. That's always the first two steps you have to do. You got to figure out the degree of the numerator, degree of the denominator when it comes to horizontal asymptotes. Now, going back to our rules, the denominator is greater than the numerator. So looking back at this, the degree, that would be part A, y equals 0 is our horizontal asymptote. And we're done. You're only ever going to have, in rational functions, one horizontal asymptote. There are other types of functions that could yield more horizontal asymptotes, but I've only ever seen one in rational functions. Okay, so once again, we've got a degree equal to 1 in the numerator and a degree equal to 2. And once again, the bottom is greater than the top. So this again would mean y equals 0 is our horizontal asymptote. So go ahead and give this one a shot. Okay, once again, I know this is pretty repetitive with the degrees. It doesn't matter if the degrees are 1, 2, 3, 4, 5. So long as the degree is greater in the denominator, you'll always get a horizontal asymptote of y equals 0. And so the exit ticket, usually I leave this to you, but this time the degrees are the same. So I'm actually want to give you an example of one where the degrees are the same. We got a degree of 1, and we've got a degree of 1. So this is what to do when you have the degrees that are the same, okay? Look at the lead coefficients and don't look at anything else. Scribble it out, ignore it. That is your horizontal asymptote. Y equals 2/3. That's what you do when the degrees are equal. We'll probably, I haven't looked too far ahead in this unit, we'll probably look at when the degree is greater in the numerator in the future, but for now, degree is less than in the numerator or they're equal are your two primary scenarios that I want you to focus on.